Hello everyone, today we have lecture number 18. And we will continue our discussion on finding expression for enthalpy of mixing in case of binary system following quasi-chemical approach. And we are trying to find out ΔHmix as a function of E and X, where E is equal to EAB, the bond energy of AB bond, EAA plus EBB by 2, and X mole fraction or atom fraction. Now, it can be expressed in terms of XA or XB for A or B with reference to A element or B element. We took a reference of BCC crystal, and if we draw a BCC unit cell, and now if I draw the atoms, so this is the center atom, and now we have to just connect this center atom with all the corner atoms, because those 8 atoms around this center atom, those atoms are acting like nearest neighbors. So, I will have bond with this. So, this is 4 bonds, and now another set of bond, this 4 bonds. So, on top we have, on top of this particular atom we have 4 bonds, and below we have another 4 bonds. So, actually we have 8 bonds. Now, if we consider Na number of A atom and Nb number of B atoms, they are in combination, they are forming N0, which is Avogadro number of atoms. So, before mixing we have pure Na, pure A atoms and pure B atoms, and in both the cases the structure is BCC. Now, pure case, pure A, if we try to find out the bonds per unit cell. So, per unit cell, the total atom is 2 A atom. So, 1/8 of all the corner 8 atoms plus 1 atom in the center. So, 2 A atoms per unit cell. Now, Z is coordination number. In case of BCC, it is 8. Since we have seen that for forming one AA bond, we need 2 atoms. So, that means the contribution towards formation of that bond per A atom is half, So, that means we can also say that the total number of bonds AA type per unit cell per A atom would be equal to 8 bonds, A type bonds per unit cell. So, we can also write Pa, which is the total number of AA bond per unit cell per A atom would be 2 into 8. This 2 is coming because 2 A atoms are there, and 8 is the coordination number by 2, because if I consider per A atom, so that means it is giving contribution of half towards that bond, towards each AA bond. So, that is where this by 2 is coming, half factor is coming. So, if I consider NA number of A atoms, so the total number of bonds would be PAA. This is, I consider this was, let us say, P prime, which is per unit cell per A atom. So, Pa would be equal to Na Z by 2. So, this is total number of, if Na is the number of atoms, total AA bond. Similarly, in case of pure B, similar situation would prevail because it is also BCC. So, that case also the total BB bond would be equal to NBZ by 2. So, this is when we consider pure A and pure B. A new situation arrives, that is when B atom as well as A atom, they mix. Let us say I consider in this particular unit cell all are A atoms, including the center atom, but one of the corner A atom has been replaced by B atom. So, this is B and all are A. So, that case we are actually having a mixture of A and B atoms. Now, we can find out the number of A atoms per unit cell would be equal to 1 for the center A atom plus 7 by 8, because 7 corners are occupied by A atoms. So, each A atom contribution would be from this corner A atoms would be 1/8. So, this should be my number of A atoms per unit cell, and number of B atoms per unit cell is equal to 1/8, because one corner atom has been occupied by B atom. Now, if we consider pure A, so that means if I consider this 15/8 is forming pure AA bond, that time P double prime AA would be equal to 15/8 into 8. Divided by 2. So, it would be again 2 PAA double prime equal to 15 and P double prime BB, I just forgot to mention this one, this would be PBB. This prime I am mentioning with reference to this particular situation. I am not considering the whole of Na atom and whole of Nb atoms. It would be again 1 by 8 into 8 half equal to 2 1. We are getting these two expressions. Now, if I try to find only A, pure A, if I assume that pure A is being contaminated by one B atom, that time the total number of PAB bond would be equal to, with reference to a par A atom, would be this. And this prime I am just mentioning because this prime indicating par unit cell. So, what is this? If I consider pure A, only pure A atoms, and then if I consider that one B atom is replacing one A atom in that pure A sites from one of those A sites, then the number of PAB bonds per A atom, this particular term is also indicating number of AB bonds per A atom. Similarly, if I consider pure B and then I consider that A is getting mixed. So, that case also P AB double prime with reference to par B atom would be equal to, would be this. So, now if I consider with reference to A, and if I try to find out the number of total AA bond plus AB bond per A atom would be equal to 2 PAA plus PAB prime. So, I can put here it is a double prime. So, everything becomes uniform. So, double prime, and this should be equal to nothing but 15 plus 1, because this is becoming 1, this is becoming 1. So, I can write another equation, number of BB bond plus AB bond per B atom would be equal to 2 PBB double prime plus P double prime AB. So, now we have to consider Na number of A atoms and Nb number of B atoms, So, in with reference to par A atom, 2 PAA plus 2 AB would be nothing but, which is again coming to be 2 into Z, which is 16, and this 2 I can consider total A plus B atoms. So, this would be again Na Z, because here I am considering 2 and Z. So, Na Z. With reference to par B atom, after mixing, 2 PABB plus PAB equal to NBZ. So, I can write it in this form. PAA would be equal to NAZ minus PAB by 2, PBB equal to NBZ minus PAB by 2. So, now just rewind back what we are doing. We are trying to see that how many bonds that could be possible if I see this particular diagram, par A atom as well as par B atom. And then after that we are trying to find AA bond type or BB bond type par A atom and par B atom, and then we are also seeing how many bonds of AB type be possible par A atom as well as par B atom. And then we are also going into another concept, that is, had it been completely A type bonds, that means there is no impurity of B in the A lattice, then we would have gotten NaZ number of bonds would be NaZ by 2 number of bonds of AA type, but since it is a mixed, so that means B impurity is coming into picture. So, PAB type is also considered, and this PAB is considered with reference to par A atom as well as par B atom. So, then we are coming to this particular equation. This is one equation, this is equation 2. And remember, this particular quantity we will be replacing in our another derived equation. Let us see, if I consider before mixing total energy would be equal to EAA into PAA, that means the total number of AA bond, EBB and PBB bonds. Now, after mixing we have AA bond, BB bond as well as AB bond. So, that time I can write it as AB PAB plus EAA PAA plus EBB PBB. So, this is the total energy after mixing. Now, we can, this particular equation we can get to E equal to EAB PAB. Now, we can replace this particular term, these two particular term from this, because this is the number after mixing. So, now if I replace it, this is the number after mixing, total BB bonds after mixing. This is also AA bonds after mixing. So, this becomes EAA NAZ minus PAB by 2 plus EBB NBZ minus PAB by 2. So, then it would become EAB PAB plus minus EBB by 2. Now, before mixing, it was all AA type or all BB type bonds. So, in case of A, the total number of bonds, AA type bonds, would be equal to NaZ by 2 before mixing. And in case of B at B crystal, we have BB bonds only, which is NBZ by 2. So, E before mixing, which is nothing but the total bond energy of the system before mixing, which is EAA NAZ by 2 plus EBB NBZ by 2. So, the energy difference due to mixing will be nothing but E after mixing minus E before mixing. So, this would turn into minus so you are getting ΔHmix equal to PAB by 2, which is nothing but E. Now, we have to find out PAB bond. Now, this E mix is nothing but the internal energy change. So, if I try to find out what would be my ΔHmix, which is nothing but it is coming from the first law of thermodynamics, which is the energy balance. Now, in quasi-chemical approach, we have assumed that this quantity is 0 and this is pressure. If this quantity becomes 0, the system becomes very simple, the calculation mode becomes very simple. So, it is nothing but ΔHmix, which equals to PAB. So, our entire attention would be now to find out PB, the total number of AB bonds as a function of x A or x B. This is the final part of the whole exercise, and once we do it, we get to know the expression for ΔHmix as a function of E and x. Let us stop here. We will continue our discussion in our next lecture. Thank you.